Have you ever heard about unijunction transistors? Neither had I until recently. In this video you will learn what these transistors can do and what they are good for. At first glance, the unijunction transistor looks like an ordinary bipolar transistor. Even its type designation is unsuspicious. 2N2646 and 2N2647 are the most common ones. They have 3 leads and come in a typical TO18 transistor package. So what is the difference? Under the microscope we can see it. A bipolar transistor has 2 PN junctions, one between base and emitter and one between base and collector. With the unijunction transistor, in contrast, the p-doped zone does not go through the entire substrate. For this reason there is only one PN junction, hence the name. The lead at the PN junction is called the emitter. You may have noticed that the emitter is not in the middle. Therefore, the connection at the longer end is called base 1 and the one at the shorter end is called base 2. Since the p-zone does not cut the N substrate apart, a small current can flow between the bases even if the emitter remains open. We can therefore model this as a diode and the intermediate sections as 2 resistors. The ratio of the resistance between emitter and base 1 to the total resistance is called the input-output ratio, or ETA for short. I will come back to this in a minute. Its symbol is similar to that of a junction field effect transistor, but it has a completely different function. To find out, let's put the transistor on a breadboard and explore what it actually does. I have built up this circuit here. Using a trim pot as a voltage divider, I can set voltages between 0 and 10 volts. Base 1 is at ground and base 2 is a 10 volt supply voltage. Between the center tap and the emitter is an LED with series resistor. I now slowly increase the voltage between emitter and base 1. Well, at about 7 volts it suddenly breaks down and the LED turns on. This means that the transistor is now conducting between emitter and base 1. When I slowly turn the trimmer back, the LED gets dimmer, hence the emitter current decreases. Actually, one would expect the voltage at the emitter to decrease proportionally to the current as well. But it increases instead, or in other words, the unijunction transistor has a negative resistance. But when the emitter current drops below a certain threshold, the LED goes off and the transistor blocks again. Now the game can start all over again. Let's take a look at the characteristic curve in the datasheet. Here we see a peak at the emitter voltage. This peak is calculated by multiplying the input-output ratio ETA with the voltage between base 2 and base 1 and adding the forward voltage of the PN junction. ETA is between 0.56 and 0.75 and the forward voltage is 0.5 volts. So if the transistor has an ETA of 0.7 and the voltage between bases is 10 volts, we get 7.5 volts peak voltage. This is about what we measured. So when the peak voltage is reached, the transistor becomes conductive. Now we are in the negative resistance region. As the emitter current continues to rise, the voltage reaches a minimum at the valley point and then rises again. Then we are in the saturation area, where the resistance becomes positive again. However, this is of no practical interest. But what is it good for now? We will get the answer if we modify the circuit a bit. I put a capacitor between the emitter and ground and remove a jumper wire. Now the LED starts to blink. And we can even adjust the frequency. We have built an oscillator with very few parts. Cool, isn't it? Okay, but what's going on there? To find out, I connect my oscilloscope to observe the voltage across the capacitor. We see the capacitor charges up to about 7.4 volts via the trimmer and the LED. So that's the peak voltage. Now the transistor becomes conductive and discharges the capacitor to the holding voltage of about 1.16 volt. There it becomes high impedance again, the capacitor can recharge and the game starts all over again. Kind of reminds me of this drinking bird. In the datasheet we find a typical oscillator circuit. If we measure the voltage at the resistor at base 1, we see narrow spikes exactly when the capacitor is discharged. These are then perfectly suited for driving power semiconductors such as thyristors or triacs. Unijunction transistors were used until the 1970s. Since then, however, cheap integrated timer ICs such as the 555 have largely replaced them. Another forgotten component that is similar in function to the unijunction transistor is the programmable unijunction transistor. Here you can see a typical example, the 2N6027. Strictly speaking, this is not a unijunction transistor at all, because it has 3 p-n junction. Thus, is it more similar to a thyristor. Also, its terminals are called cathode, gate and anode, but the gate is attached to the N layer. This is the difference to the thyristor, where it is connected to the P layer. Its symbol also looks confusingly similar to that of a thyristor. The difference here is that the gate terminal is drawn on the anode side. The voltage current curve between the anode and cathode looks just like that of a unijunction transistor. Again, we see the maximum at the peak voltage and the negative resistance. But here it is that the peak voltage depends on the gate voltage. To show this, I have set up this oscillator circuit here. Now I measure the voltages at the anode and the gate. At the anode we again have a sawtooth wave, and at the gate we have a DC voltage, which is pulled to zero for a short time by the gate when the anode becomes conductive. I overlay the two waveforms on top of each other so we can compare them better. With the trimmer I change the gate voltage. And now we see that the maximum of the anode voltage changes with the voltage at the gate. With it, the frequency also changes because the capacitor is discharged earlier or later depending on the peak voltage. There is a small offset of about 0.4 volts, so peak voltage is equal to the gate voltage plus offset. So you can say that the transistor is programmed by the gate voltage. Of course, this is not classical programming as we know it from microcontrollers. With the help of programmable unijunction transistors, you can easily realize a voltage-controlled oscillator. With the peaks that can be tapped at a resistor at the cathode, you can toggle a D flip-flop and get a clean square wave voltage with constant amplitude, whose frequency can be controlled with the gate voltage. So, I hope you enjoyed the video. If so, give it a thumbs up, feel free to check out my other videos and subscribe to the channel and activate the bell, so you're always up to date. By the way, supporters on Patreon can enjoy ad-free videos and previews. Try it out. Thanks for watching. See you next time.